everyone. Today we will be covering the last part of the petrochemical industry, which is aromatic uh, chemical compounds that we'll be discussing in this class and try to cover all of the major aromatic compounds that we can cover up in this syllabus. So let us start with petrochemical industry. So what are the chemicals that we can expect to be uh, derived from the aromatic compounds? So first of all, the main aromatic compounds for various chemical synthesis are majorly BTX, which is B for benzene, T for toluene, and ZX for xylene, and also naphthalene is there. So these are the some key or main aromatics for the uh, whole aromatic compound. The you can say that these are the king components. Okay, we can derive lot of other chemicals, lot of other aromatic compounds out of this benzene, toluene, and xylene. So this BTX is very important term in in terms of the aromatic whole lot of compounds. So, what are the primary sources for BTX? Primary sources are we can use oil, petrochemical oil, as well as coal. These two are the sources of primary. We generally consider it to be the main source for BTX. If you go for the coal carbonization gives volatiles during the coking operation, which is stripped of tar by electrostatic precipitator method and then is scrubbed with the dilute sulfuric acid, which is 10 to 20% acid, to remove the ammonia, and the remaining crude benzene fraction is then absorbed in a high boiling stable oil such as creosote. Okay, then this creosote oil has a proximate composition of BTX. The composition is 60% benzene, 15% toluene, and 7% xylene, and rest of the 4% around naphthalene is there, and solvent naphtha is also present around 7%. So you can see that coal is the primary source, and by the coal carbonization, the whatever product we are getting, that is first from there the tar is separated, then it is washed with uh, sulfuric acid, and then the remaining benzene fraction is then categorized as proximate analysis. This has BTX and naphthalene as well, right? The production of the aromatic raw materials from the petroleum crude oil is derived from which processes? First process is solvent extraction of distillate fractionations. Second process is reforming of the fractionating the reformates. Third process that we can derive BTX, that is naphtha cracking process. Fourth process is hydrodealkylation process. This process is very important. Now next, we see that the major use of the benzene is for the production of phenol and as well as styrene, with the remaining approximate around 40%, which is divided equally among other aromatic derivatives such as aniline, sulfonated detergents, DDT, malic anhydride, chlorobenzene, and chlorohexane. Right? Chlorohexane comes from also petroleum crude oil via catalytic hydrogenation method. WAF, catalytic hydrogenation of benzene, and direct fractionation of reforming stocks. So it is a very important intermediate cyclohexane in the synthetic fiber preparation. Now 6,6 nylon, which is a very popular fiber, is produced by the oxidation process of benzene to adipic acid, which is then condensed with hexamethylene diamine to produce the nylon fiber. So nylon fiber is basically, it can be derived from benzene. Another one BTX, so T for toluene. Now the toluene is produced in equal yield that of benzene and that of xylene in the petroleum refining operations. Toluene is majorly used as solvent in case of paints, rubber, plastic cements. It is also used as a detergent like toluene sulfonate, and also some chemicals in like plasticizers and others. There is major uses of toluene. Toluene is also used as a blending material in the motor petrol to upgrade the octane number to reduce the knocking property, and this produces low income yield as fuel value. Also, toluene is used in the production of the phenol, and the dealkylation process of the toluene with the hydrogen is used to produce benzene. So, from the toluene, we can also produce benzene by dealkylation process with hydrogen. So, the primary source of the toluene is the catalytic reforming of the refinery streams. This source around 87% of the total toluene produced. An additional 9% is separated from the pyrolysis of the gasoline produced in a steam cracker during the manufacture of the ethylene and propylene. So there, the major portion it is coming from catalytic reforming of the refinery streams, but some of the additional portion of toluene is also we are getting from pyrolysis of the gasoline. Now the next is xylene. It is also a low value, high octane blending fuel, just like toluene, right? And almost 60% of the xylene is used for this purpose, for the blending of fuel. Now the xylene is also used as solvents, high boiling type in largely alkyl resins, and the chemicals like phthalic acid, isophthalic acid, dimethyl terephthalate. So for these cases, xylene is hugely used. Naphthalene is also majorly derived from coal like heavy naphthalene, heavy portion. 80% of this naphthalene is used for the production of the phthalic anhydride. Also, hydrodealkylation process of the petroleum crude oil is also used for the sufficient supply of the naphthalene in the market. Now this can you can see from this figure that what are the synthetic chemicals and the intermediates you are getting from aromatic compounds. So these are the main aromatic compounds, that is B, T, X, benzene toluene xylene, naphthalene, cryolic acid, some other compounds are there. So from the benzene, we will discuss later on how to produce styrene. So from the benzene, we can have styrene. From the styrene, it is usually used in the rubber industry. You can see S-type rubber, S-type latex, reverse ratio rubber, polystyrene. So this kind of thing we can derive from the styrene, which is mainly produced by from benzene. Okay, from the benzene we can have dodecyl benzene, which is used to make detergent. From the benzene we can also produce phenol, which is used usually in the nylon making. Also we can derive DDT, malic anhydride. So some of the production of these compounds from the benzene um, we will be discussing further. So just like toluene is usually hugely used in solvents, coatings, benzoic acid production. So from there it produces sodium benzoate. Xylene, orthoxylene, metaxylene, paraxylene. So this kind of thing it produces anhydride, phthalic anhydride, isophthalic acid, terephthalic acid. Naphthalene, it is phthalic anhydride naphthanol intermediate insect repellents it is used. Cryolic acid in the resin or molding plasticizer disinfectant it is used as. Copper naphthalate it is usually used in anti-fouling paint, and metal naphthalate is paint dries. These are the something where in the mostly in the paint industry and pesticizer industry, as well as synthetic rubber or this kind of resins making industry, aromatics are hugely used. Okay, so we will be now discussing what is the hydrodealkylation process that I already discussed that this process is very important. So it is a method of converting all the toluene and dialkyl benzene to benzene. Ultimate goal is to produce benzene. Can be made from alkyl naphthalenes by the same process also. Now the competitive process here, non-catalytic thermal process and also catalytic thermal process, two types. Now the catalytic process, because of the presence of the catalyst, they can be operated at a lower temperature and pressure in compared to non-catalytic thermal process. Now hydrodealkylation is a very low cost process, feasible method to convert all the unwanted toluene to benzene by the hydrodealkylation method. The process is readily handled within the refinery operations so that high grade benzene is available to the consumer plants in the immediate vicinity. It is very feasible method. So we will now discuss that what are the chemical reactions involved in the dehydroalkylation process. So from here we will have first toluene as a reactant, C6H5CH3. So this toluene it reacts with hydrogen, so it forms benzene and methane as well. Then it also reacts with hydrogen and it also forms benzene. Similarly, higher aromatic compounds, these all can react by this process X number of hydrogen and it reacts. So these reactions are involved in hydrodealkylation process where mainly the benzene we get as a product. So we will now discuss this dehydroalkylation process of the alkyl aromatics. Suppose here we are taking um, toluene. So from toluene we are producing benzene as a our ultimate product, right? So in this flowchart, what we can see that we are feeding alkyl aromatic as a feed. It is also mixed with some hydrogen source, and also along with some recycled gas is there. So now they are compressed by the compressor, and then it is preheated. This is the preheater. It should be preheated or preheated. Also you can see that for the preheating you are using external fuel, that is burnt preheater. So after that the mixture alkyl aromatic feed, hydrogen gas, and also some amount of the recycled gas is mixed up, and then it is fed to the reactor, right? Now this reactor that we already discussed in the last slide, that this can be two types. One, it can be fixed bed catalytic reactor, right? Fixed bed catalytic reactor. Or another one, it can be tubular non-catalytic reactor, right? So any of these two type can be this reactor type, and then after the after the hydrodealkylation occurs in the presence of the hydrogen, the product will be passing through the same preheater. The heat exchange will be performed, and it will be cooled down, right? Cool down, and again it is again cooled down by water circulation through the chamber, and then it comes to the high pressure gas liquid separator. So it is operated at a very high pressure condition. Okay, so here the liquid and the gas is separated, and from the gas section you can see that there is hydrogen and CH4 mixture, right? In the equation also we have seen that in the every equation of hydroalkylation process, there the methane is produced a lot of amount, right? So this hydrogen and methane, that mixture, further it can be considered to be further used as a fuel. Otherwise it is sent to the methane separator. So from there also hydrogen can be regenerated and it can be reused in the process, and methane can be used in the further fuel. So some of the portion of this gas can be recycled at this feed point. So this is the gas section, and for the liquid part it is taken to the gas stripper. So in the dissolved gas, whatever be there in the product, so that will be stripped, and at the top the gaseous product that is collected, that will be have good amount of good quality of fuel that it can be used from that, and the liquid portion is further taken to the fractionator. It is operated at a low pressure condition. Okay, and then from here as a top product we are getting benzene as our desired product, right? So this benzene is of very high purity benzene, and here the high purity in the sense the thiophene content here is less than 0.5 ppm. Okay, now as a bottom product of the fractionator, we are also getting heavy end purge. So this can be further taken, recycled. Those have high alkyl aromatics. Those can be recycled back with the alkyl aromatic feed. So by this process, the 95 to 98% conversion can be found out for a toluene as a feedstock, and 90 to 95% conversion is found out for naphthalene as a feedstock. Okay, so that's how by hydro dealkylation process we are getting benzene from the alkyl aromatics, various alkyl aromatics product. So we will be now discussing what are the major engineering problem that is associated with the hydrodealkylation process of the alkyl aromatics. So the first problem is the catalytic process. Those are operated at 600 to 650 degrees Celsius and pressure of 35 to 40, whereas the thermal hydrogenation process generally those are operated at a very high temperature and high pressure condition. But the both processes has comparable yields. Economic balance in a reactor design, those should include residence time, temperature, recycle rates, pressure, and throughput capacity and vessel cost. Ample amount of the hydrogen is available from the reformer, and methane composition of the charge gas and the parts rate are fixed by the reactor kinetics. Hydrogen handling requires explosion-proof plant construction always, and it uses in equipment at high temperature condition and the pressure dictates chrome steel to avoid the embrittlement. So we will be now moving forward for the production of the phenol. So phenol it can be also produced from the benzene, right? The first thing is the largest use of the phenol in the plastic industry. To produce the thermosetting resin made with the formaldehyde. Less than 15% of the all phenol production comes as a phenol from coal carbonization plant. There are 7 processes for the synthetic phenol preparation, and out of which only 6 are still competitive, and the 7th one is not that much non-commercial. So, what are the 6 competitive commercially available processes for synthesis of phenol? First process is cumene peroxidation hydrolysis process. Second process is toluene two-stage oxidation process. Third is Raschig vapor phase hydrochlorination and hydrolysis process. Fourth one is chlorobenzene caustic hydrolysis process. Fifth one is benzene sulfonate caustic fusion process. Sixth one is benzene direct oxidation process. So we will be discussing all of the processes one by one, touching upon all the key flow sheet to describe the whole process very briefly. The other non-commercial non-commercial process of the phenol production, that is chlorobenzene soda ash hydrolysis. So we will be discussing this commercially competitive these 6 processes. Okay. So the first process we are going to discuss, that is the cumene peroxidation hydrolysis process. So cumene we already discussed in the last previous classes, one of the previous classes, that cumene that is isopropyl benzene made by alkylation of benzene with propylene, right? Now chemical reactions those are involved in the process. So what are the chemical reactions? First reaction, that is peroxidation reaction. Where the cumene is reacted with air, it forms cumin hyperoxide. Kind of this. So this one is cumin hyperoxide. In the next process, this cumin hyperoxide is hydrolyzed. So the process name is hydrolysis. So this one is getting hydrolyzed in the presence of aqueous sulfuric acid and it produces phenol. Plus, as a byproduct, we are also getting useful product of acetone. Phenol and acetone we are producing out of this cumin peroxidation and hydrolysis method. First step is peroxidation process. Second step is hydrolysis process. So in this flowchart, we will be discussing that how from the cumin we are getting phenol as a main product and acetone as a byproduct. So we are putting fresh cumin as well as some amount of the recycled cumin at a ratio of 1 is to 4. Okay, it is fed as a feed and then it is also mixed with air in the oxidizer. In the presence in the presence of the sodium carbonate is used at a pH of around 8.5 to 10.5 pH is maintained. So in the oxidizer, the oxidation of cumin to cumin, hy- cumin hydroperoxide is being done. Some of the vapor is condensed and back to the oxidizer. The liquid product is taken to the cleavage. Why? This is a very uh, stirred kind of reactor where the temperature is maintained at 55 to 65 degrees Celsius. And this is here the sulfuric acid is being fed to do the hydrolysis of the product that we discussed earlier by the reaction, right? So that we will get the phenol as a product. This sulfuric acid is a weak sulfuric acid, 10 to 20% concentration from the product, whatever the product is stream. This is kind of mixture of phenol, acetone, even alpha methyl styrene, also some unreacted cumin and acetophenone. These are some mixture of components that we are getting at the last of the hydrolysis reaction occurring in this cleavage, right? That is taken to the separator. From separator, here the heavier some of the portion is being recycled by the and the upper portion is taken to the washing section where it is washed by water and the acidified wash water is separated out from the bottom of this wash tower. Now this crude phenol, whatever is producing from this tower, is being washed and it is then fed to the distillation column where the where the volatile acetone is being separated as the top product and the bottom product of this distillation column is taken to the vacuum distillation column. Okay. So to avoid the heating kind of distillation, we are maintaining the vacuum condition here. So from here we are taking we are getting the cumin. Cumin is being separated and it is kind of methyl styrene is also separated as a top product, and the some of the mixture. Okay, so cumin is being separated here in the first vacuum distillation, and the bottom product is sent to the second vacuum distillation column where it is methyl styrene is separated. So this recycled cumin and the methyl styrene, these two can be used further, so that it is first sent to the hydrogenation process or hydrogenator. Here the hydrogen is being fed here where the nickel catalyst is used for hydrogenation process, right? Now that hydrogenation is being done because this methyl styrene and some cumin unsaturated any kind of compound is completely saturated before putting to the oxidizer. Okay, so that decomposition of the peroxide during the oxidation process can be avoided. So after the separation of cumin and the methyl styrene, the rest of the product is sent to the further vacuum distillation third, and from there as a top product we are getting the phenol as a passing through the crystallizer, and as a bottom product we are getting acetophenol. Okay, so we are getting product as acetone, acetophenol, and phenol. So this is a very useful. Uh, so this process I didn't write here. This process is known as cumin peroxidation hydrolysis. Right? Okay. So, what are the major processes, major engineering problem involved in the phenol production from the cumin? One is the intimate dispersion of the air bubble with the emulsified hydrocarbon water mixture is very important in attaining good conversion and low loss of the hydrocarbons through the vent gases. Right? There should be good combustion because in the oxidizer you have seen that air is bubbling up, so there should be good mixing. Otherwise there will be loss of hydrocarbon through the vent gases, so this should not happen. To get a good conversion we should avoid that. Now the cumin hydroperoxide is very explosive in nature when it is allowed to accumulate a lot. Okay, so the reactor design should take care the fact that it is avoided the trapping of the condensed liquid at any large amount. Next process we are going to discuss for the production of phenol, that is toluene oxidation process. That is one of the commercially available process, also competitive process for the phenol production. So this process is toluene oxidation process. So what are the chemical reactions involved in the toluene oxidation process? We will get oxidation first. We will do the oxidation of the toluene, right? So the first process is oxidation to benzoic acid. So we get toluene, we do the oxidation at 150 degrees Celsius in the presence of the cobalt, naphthalate, and we get benzoic acid. And the second step is oxidation of that benzoic acid to produce phenol. So this is a two-step method. So we are taking here the benzoic acid. It is going for oxidation in the presence of cupric benzoic acid at 220 degrees Celsius. Cupric benzoate as a catalyst, and we get phenol. And carbon dioxide is also produced. So these are the simple chemical reactions involved. So this process is called toluene oxidation process. It is also known as two-stage method. Why? Because there is two stage of oxidation that is happening. So in this process of two-stage oxidation process, the toluene Toluene with the catalyst is fed in the reactor, where air is also bubbled up in the stirred reactor. The rest of the product is taken to the separated, fractionated, or you can say, from where the top portion is toluene. Toluene is some of the portion is recycled to the first step of feed. Okay, the bottom product of the distillation is taken to the stirred tank reactor, where the hot water is being fed. So here the hot water is used to see, this is the first oxidation process in the presence of the air, or you can use air also, or it will be also as a work, it will also work fine. And then it is fed, benzoic acid is being washed here by hot water, is crystallized, and then benzoic acid is further washed. So before putting it to the, it can be taken to the through the melter, where it is melting up, and then in the presence of the, for second oxidation process, it is in the presence of the cupric benzoate catalyst around 200 degrees Celsius, it is passed to the second oxidation, right? In the second oxidation, at the top product, there are some benzoic acid which is recirculated the after separating out of from here. And then at the this gas liquid separator, here we are getting some of the CO2 CO gas. Okay, and then in the bottom product of this oxidation reactor, it is taken to the heavy end, that is tar. Now in this reactor, the separator at bottom product is taken crude phenol. Crude phenol is being produced by this oxidation, second stage oxidation process. So this crude phenol is further taken for the purification, and from there it has lot of water content, so it is passed to the azeotropic distillation column, so that water is being uh, uh, removed from this crude from this phenol, and this phenol product is taken out as a product, and some of them are recycled back for reducing the water content of it. So this is a very simple process, two stage process, because there is one oxidation process and there is two oxidation process, so that's why this is a two step process. So further moving, next commercial process, that is the Rashtig phenol process using the hydrochlorination of the benzene. What are the chemical reactions involved in the Rashtig phenol process using the hydrochlorination of benzene? Very simple reaction. First one is the hydrochlorination process. Here the benzene is reacted with the HCl and in the presence of oxygen at 240 degrees Celsius and ferric chloride and cupric chloride um, catalyst, you are getting chlorobenzene, monochlorobenzene and water. In the second step, that is hydrolysis. So hydrolysis of the monochlorobenzene, it is hydrolyzed at a temperature of 350 degrees Celsius where SiO2 catalyst is used and we are getting out of there phenol and HCl is produced that can be recycled. So very simple two steps of reactions. So now we will discuss the flowchart for this reactive phenol method. So in this process, what we can see that the benzene is first sent to the okay. So the process start here. The purified benzene is fed to the hydrochlorination reactor, where the reactor temperature is maintained around 240 degrees Celsius, and from this hydrochlorination process, we are getting the monochlorobenzene and some of the other benzene uh, other chlorobenzene forms. So those are taken to the fractionator. So at the top, the lighter portion of the phi here represents the benzene part. So crude monochlorobenzene is being separated as a top product and it is fed to the scrubber where it is scrubbed. And here after scrubbing, it is further sent to the second scrubber and the phenol is being separated. This phenol is this phenol as a top product. It is separated and sent to the extractor, where the some of the part is extracting. After the extractor, the circulating water is being sent to the scrubber for further scrubbing, and the top product of the scrubber is from the distillation column, and from the distillation or fractionation, whatever it is, and now it is coming to the phenol purification process, where we are getting phenol as a bottom product. And here, in the process of a hydrolysis reactor that we discussed, that this monochlorobenzene is fed to the hydrolysis reactor, where we get HCl as a byproduct and also phenol as a main product. That phenol is being uh, generated from the hydrolysis reactor, which is fed to the scrubber, and then scrubbing, and then it is goes in that portion of the setup, and then it is phenol purified form. So ultimately we are getting purified phenol. So this is very simple method, but the thing is, the process flowchart is looking very complicated, but it is not complicated as of now. This is very simple. If you know, if you remember the two reactions mainly, one is hydrochlorination reaction that is occurring in this place, in this reactor, and second part is the hydrolysis process that is occurring in this reactor. So other part is, you know, that what are the reactants and what are the products. So you can also simplify this whole flowchart, which is looking little bit of complex, but it is not as much complex that it seems like it is shown. Okay, so we are going forward with the next process, that is chlorobenzene caustic process for phenol production. So in the next process, that is chlorobenzene caustic process for the phenol production, this is also a process where this is commercially available and very competitive process. We will discuss the flowchart of this process in details. So let's move on to the chemical reaction part for this process. I will write it down. The first part is chlorination part. It's very clumsy, so. So, in the chlorination part, the benzene is reacted with chlorine at 85 degrees Celsius, presence of Fe or FeCl3 catalyst. It produces monochlorobenzene, Cl. In the second process, it is done causticization, where the monochlorobenzene reacts with caustic soda, that is NaOH, in aqueous condition, and it forms sodium benzoate. In the third process, that is hydrolysis process, this sodium benzoate is reacted with HCl aqueous and it forms phenol, and it produces NaCl aqueous phase as a byproduct. So it involves three steps. First step is chlorination, second step is causticization, third step is hydrolysis. So by this flowchart, you can see this is the chlorinator reactor, first reactor. So we are putting benzene, and as a catalyst, if you have FeCl3 catalyst, it is happening at a reaction of 85 degrees Celsius. So here we are also putting NOH as a, sorry, it is later on. Okay, so in the chlorination part we are getting monochlorobenzene. So that part is taken to the next step of preheater and all. In the meanwhile, it is 10% NOH is added because it is being prepared for the next step, that is causticization process. So it is being taken to the reactor where 550 atmosphere temperature is maintained, and this reaction temperature is also had to be maintained by, at 425 degrees Celsius. So from the reactor, it is taken to the causticization reactor. It is taken to the neutralizer where the um, some of the ACl off gas from the it is being neutralized by ACl, and then NaCl feed is NaCl as a NaCl is separated out, that can be fed to the electrolysis cell. Okay, the further it is taken, the product is being taken to the vacuum column. Okay, from here the fractionation is occurring, and as a top product of after the steam washing, we are getting phenol as a product. As a part of the vacuum distillation column, we are getting diphenyl oxide, which is can be sold or recycled for the further processing. The next process that we are going to discuss, that is the benzene sulfonate process to make phenol out of benzene. So the chemical reactions involve four steps to produce phenol from benzene by this process. First step is sulfonation process, where benzene is reacted with sulfuric acid, which is very high concentrated sulfuric acid, and it forms benzene sulfonic acid. Next part is neutralization process, where the benzene sulfonic acid, it reacts with Na2SO3. It produces sodium benzene sulfonate. The third step is the fusion, where it is further reacted with NaOH. That is the fusion reaction at a temperature of 300 degrees Celsius, and it produces sodium benzoate SO2. And the last step is the acidification process, where the sodium benzoate, it reacts with the sulfuric acid, and it produces phenol. At the last, also some of the thing that you can recycle it and reuse it in the process, right? So it has four steps: sulfonation, neutralization, fusion, and acidification. We will now discuss the process flowchart for benzene sulfonate process. So in this process, the benzene is being preheated and it is sent to the first process, that is sulfonation process, continuous sulfonator it is sent, where the concentrated H2SO4 acid is also passed in the reactor. The product is being sent for the neutralization, where it is neutralized by Na2SO3, and where the SO2 gas is being produced as a byproduct and it can be used as a further step. So the further process, the which is produced sodium benzene sulfonate, so that is passed to the pressure filter, and from here Na2SO4 is being separated. Further product is taken to the fusion process, where it is reacted with the NaOH at a temperature of 300 degrees Celsius, and the product is taken for the acidification reaction, where the diluted H2SO4 acid is used, and also the SO2 is also used in the acidification reaction. The product, the top product of this is taken to the vacuum still, where the phenol is collected as a top product and waste, the heavy product, is separated out, and the further product from the acidification reaction is taken to the stream stripper, where as a bottom product we are getting N2SO3 as a, that can be recycled back to the neutralization step. And other thing is this some of the product from the top product of the steam stripper, it is again some of the phenol is separated out from this stream, and it is collected in this stream, while it is sent to the vacuum still, and as a top product we are separating out phenol. The next process we are going, and the last process we are going to discuss for the production of the phenol, that is direct oxidation process. So the chemical reactions involved in the direct oxidation process, that is benzene, it is reacted with the hydrogen, so it forms C6H12. It reacts with further oxygen, and it reacts with, and it forms C6H11OH. These reactions happen, and further from here we get phenol out of that and hydrogen. So here what happened, you can see that first benzene is hydrogenated to cyclohexene, which is further oxidized in the presence of oxygen or air, and it produces the mixture of cyclohexanol, cyclohexone, and unreacted cyclohexane. The unreacted cyclohexane is separated and can be recycled. The oxygenated fraction is then dehydrogenated by this process to produce phenol at the presence of nickel or platinum catalyst. Though the direct conversion of the phenol via air oxidation has been subject of much research because of its simplicity, right? This is very simple. But the yield were never so high that much. This process is not so much used in the industry or full commercial scale. So next part we are going to discuss, that is production of styrene. Styrene, that we know, this is this kind of structure, CH CH2. Okay, so first is method of production. So there are two methods of production. One is dehydrogenation of ethyl benzene. Next one is hydrogenation and dehydration of acetophenone. So the chemical reactions involved in the dehydrogenation process, that we are going to discuss. The first process. First one is alkylation of the benzene. So here the benzene, it's react with ethylene, right? In the presence of the AlCl3 catalyst, also there is ethyl chloride. It forms ethylene, ethyl benzene. Next part is the dehydrogenation of ethyl benzene. So this ethyl benzene, they react in the presence of this catalyst at a 1500 Fahrenheit temperature, and it forms a styrene. So this is styrene, I already discussed. Also hydrogen. So this method is endothermic. Delage here is 28.1 kilocalorie. So this is the endothermic process. We are going to discuss the flowchart of styrene production from benzene and ethylene. So in this process, we can see some wet benzene. We have to first dry it over azeotropic dryer. So after drying, it is sent to the alkylation reactor. So first reaction is the alkylation of the benzene, right? So we are giving here the benzene, and also we are putting ethylene and uh, ethyl chloride. In the alkylation reactor, we are also putting this catalyst. So from the alkylation reactor, we are getting ethyl benzene. So ethyl benzene from here. AlCl3 complex is recovered and that can be recycled. And after that, this is high temperature dealkylated, where the residue has been collected. So it is being used at a later part, whereas this from this reactor, the ethyl benzene is collected and it is after heat exchange, it is sent to the dehydrogenation process, where the 50% NaOH is also used because it is being caustic wash. Then it is sent to the stripper, and from the stripper, the benzene column at the top product benzene is being recirculated. Also, it is passed to the azeotropic dryer every time to dry the benzene. It should not contain so much of water. So from the benzene column as a bottom product, the ethyl benzene is being separated out, and as bottom product it is can be again recirculated back to the alkylation reactor. As a top product, the it is 20% NOH is being it is washed again, and from the dry we are getting dry ethyl benzene, which is being ready now for the next step. In the next step, it is fed to the again it is preheated and it is sent to the catalytic dehydrator unit. So this temperature is maintained 800 degrees Celsius, and this maintaining temperature is very important for this process. So the top product is being sent to the quench tower by the steam it is being quenched, and it is further sent to the benzene column. For the benzene recovery, the top product is the bottom product is taken to the ethyl benzene column. Again, the ethyl benzene is being separated out and it can be circulated back, and the bottom product is taken to the flashing column. Where from the flashing column, the top product is the styrene, our required product, and the rest of the tar in heavy end, that is the tar, it is being stored as a tar, or it can be used as a batch tar still. Uh, so from there, uh, this section we are getting styrene as a product, right? The next we are moving to the next production of the phthalic anhydride. So the major uses of the phthalic anhydride is alkyd resin and plasticide. Okay, the method of production of the phthalic anhydride, that is oxidation of the naphthalene or orthoxylene. What are the chemical reactions involved? So the chemical reaction involved a lot of steps. First one is first step is uh, naphthalene oxidation process in the presence of V2O5 catalyst. Second step is orthoxylene oxidation process in the also presence of the V2O5 catalyst. Third, some side reactions are occurring because of the complete conversion process, and the minor side reactions are occurring where the malic anhydride are produced as a side product. So side products are malic anhydride. So you can see from this naphthalene or orthoxylene is being fed, and it is melted before feeding. So there is fluidized bed at the top. It is sent to the uh, dust cleaning, and it is sent then steam. Then the tar, the heavy end product is being separated out. Then the next step is the fluidized bed condenser, where the vent gases is sent for the well water scrubbing, and from here only we are getting phthalic acid. This is very simple reactions. There is nothing like complicated. The next process is malic anhydride process, that we already seen that malic anhydride can be uh, produced as a byproduct from the ferric anhydride process production. So production of the malic anhydride, the first one is the major uses of the ferric anhydride is in the polyesters. Now oxidation of the benzene and in butane, that is the method of the production. We are going to discuss this process. So chemical reactions involved sorry in the oxidation this process. First one is the benzene oxidation occurring. Which is a very exothermic process. Next step is butane oxidation process. So from this, the malic anhydride is produced. It is also an exothermic process. We can see two reactions are occurring. So from here you can see this is a tubular reactor where from the benzene you can also use, from the butane you can also use. So if you are using benzene, then you have to make a vapor. If you are using butane, then you don't have to make a vapor out of that. So it is mixed with the air and it is preheated and sent to the tubular reactor. Here the fused soil is used or saturated to maintain or control the reaction temperature at a certain temperature. Now the product is taken to the after tart separation. It is taken to the scrubbing. Water scrubbing is there. Then the dehydrator is there. Then the vacuum refining. So here, as a bottom product of the dehydrator, we are getting 40% of the malic acid solution. From here, the malic acid solution we are getting from this water scrubbing. Malic acid solution is taken. Some of the part is taken for the isomerization, and we are getting fumaric acid out of that. And here the vacuum refining process. Here the after cooling down or chilling, we are getting malic anhydride out of that. So this is a very simple. So that's it for aromatic compound. We are closing it here for today's session. So we have already gone through three lectures, I guess, for overall petrochemical industry cover all of the parts. Uh, so today I have completed the aromatic parts as well. So from the next class, there will be class on next week Monday. The class has been preponed. It will be announced very soon. So next week Monday, I will be taking class on the same time slot, 7 to 9. So at that class we will be discussing a new chapter that is left in the syllabus, so we will cover that. So till then, this is up to this class. We have already covered and finished petrochemical part. So we will meet in the next class. Okay, bye.